Welcome everyone. Let us start the second session. First speaker is Suravi Pal. She will be talking about equilibrium and transient behavior of modulated binary colloid.
A very good afternoon to everyone. I shall be speaking on equilibrium and transient behavior as she already mentioned. I have carried out this work under the supervision of Professor Joydev Chakraborty from SN Bose. The audience here needs no introduction to colloids or the work that I work on here. I primarily work on colloidal system, monodisperse or bidisperse under external modulation. Here there have been many experimental studies as well on binary colloids. One such example to name is one where they have taken a quasi 2D experimental system with polystyrene beads of two different sizes, one having the diameter twice that of the other ones. And they subjected the system to an external modulation, laser beam, one dimensional laser beam, where the wavelength of the laser beam matches with the diameter of the bigger particles. As a result, the bigger particles get aligned along the potential minima and the smaller particles get arranged within the cavities of which bigger particles make. So, but there have not been much study on the phase behavior or dynamics or kinetics of such a system. So, our objective is to probe into that. We take a system of a two-dimensional system with two different type of particles, one having diameter twice as that of the bigger one, which interact via this kind of repulsive potential, where epsilon alpha beta is the interaction strength, alpha and beta being the signifying the two species. We take small and big interaction to be 1, but small epsilon big bs, the big small interaction, to be 1.5. So different species repel more. Then before anything, we simulate the system using Monte Carlo simulation, and we observe that big clusters of the smaller particles, the red ones here, form within a background of the bigger ones, the blue ones. This is of course due to this interaction potential that we take. Now we subject the system to such an external modulation where the lambda, the wavelength, matches with the diameter of the bigger particles. So, as a result, the bigger particles get aligned along the potential minima, whereas the smaller particles are not faced upon by such a magnitude of force due to the potential as similar that of the bigger ones. So, they get aligned within in between those bigger particles, as if the bigger particles get aligned along the potential minima by breaking the big clusters of the smaller ones. As a result, the system goes from a phase separated demixed state to a modulated mixed one. Now we are saying that there is a phase transition going on from a demixed one to a mixed one. So we associate order parameter with the phenomena. How do we consider an order parameter? We consider a rectangular box anywhere in the system, here or here, anywhere, and we calculate the difference between the numbers of bigger particles and the smaller particles within that very box. Now, if we before we do that similarly for after the transition has taken place, and we look into the number difference. Initially, in absence of any external modulation, that would yield a high value of order parameter value, because in a particular box there would be one type of particle more residing there. But in the case of mixed modulated state, there would be almost equal number of bigger and smaller particles. So we plot the average order parameter versus the strength of the external modulation. We observe that the order parameter gradually decreases, but following a jump at a certain point. So we calculate the specific heat of the system, and we observe that a peak arises at specific heat at that very discontinuity, the point of discontinuity. So to look into whether the nature of this kind of transition, phase transition that is going on, we simulate for different system sizes, one being smaller than the results that I have uttered here, and another one being much larger. We observe that similar phenomena occurs, and the peak in the specific heat gets more and more shifted. Also, the heat capacity varies with the number of system size almost linearly. This jump in the order parameter increases with the system size. So, definitive of the fact that the transition from demix to the modulated mixed state is accompanied by a first order phase transition. Now we start and look into the kinetics of the system. So we start from the mixed modulated state, turn off the external modulation, and let the system evolve in time via BT simulation. So we observe that in time, gradually more and more clusters of smaller particles are gradually coming into the scenario again in a background of the bigger particles. This is the density plot that correspond to that. We look into the cluster size, how the cluster sizes of the smaller particles evolve in time. We observe that gradually it increases before coming to a saturation to as the system reaches the equilibrium value. We call that very time to be the transient time, where the cluster size had attained half of the maximum value. We look into various dynamical properties and structural properties within this transient state. One thing to note, that since the system is continuously evolving in time in the transient state, we could not take any time averages of any of the variables that I am going to explain in next minutes. So we only could take sample averages or noise averages over different BD trajectories. First, we look into the aspect ratio, which is the ratio of radii of gyration along both the direction. We observed that the clusters were initially elongated in y direction, which was also evident from the configuration. Next, we observe that gradually as the time as the system reaches the equilibrium, the clusters are forming more and more compact circular-like object, circular-like structure. Now we look into the dynamics. So we look into the mean square displacement, both taking into account both the species. These two panels are for the bigger ones, these two panels are for the smaller ones. Whereas the bigger, we plot the mean square displacement for bigger particles here, starting from different initial time. That is because no two information in no two time is equivalent here. So we calculate the diffusion coefficient from the mean square displacement, slope of the mean square displacement for both the cases. Here for the longer time displacement, we observe that for the bigger particles, the the diffusion is gradually increasing for the bigger particles, whereas for the smaller particles, initially up until the transient time, there is not much diffusion occurring in the system, because the particles are now more focused on forming the clusters. After that, the diffusion of the smaller particles gradually decreases. So it's as if slower moving clusters are forming of the smaller particles are forming in a faster moving background of the bigger particles. So this was the results that we get from the kinetic study. So to conclude, we look into the phase behavior and kinetics of a system in presence and in absence of the external modulation. We observe that the smaller particles gradually form clusters in absence, and when we also switch off the external modulation, the cluster gradually grows in time. So that's to conclude. I thank both my supervisors, the lab facility of SNMOS, National Center for Basic Sciences, my past and present lab members, and of course the organizers for letting me share the stage in front of such a brilliant minds. Thank you.
Now we have quick questions.
And so it looked like the small particles, they're kind of stuck in these clusters, right? And like you have these red clusters, those are the small particles.
Yes.
But and how come they're still diffusing? Like it depends probably on the surface, guys. The inside, deep in the cluster, they look kind of stuck, right? But how come you have
no, I mean, if I could show many more intermediate configurations here, then it could be like more visible that they are moving before reaching. Of course,
so the time scale is over.
Here, the cluster size gradually increases before coming to saturation value.
So, okay, so this is during the growth process.
Yeah, this is during. I am looking at the kinetics during this transient state where the clusters are gradually growing.
And other question was, why doesn't it form a glass? Like usually you hear that if you have binary mixture, it forms a glass.
So you mean complete demixing, or like that is two reasons. One can be is that because of
The initial concept.
because of this interaction parameter that I am here focusing on the cross-species interaction, but the intra-species interaction is also repulsive. So once the particles are within, say, large enough clusters, they cannot hop into another cluster so easily, because to demix completely, you have to be feasible, the dynamics have to be diffusive feasibly there, and entropically also this will be much more favorable.
Yeah, can you just show your cluster size growth law? So this is C is number of particles in the cluster. What is CFT exactly?
No, C is the cluster size. Yeah. Number of particles.
Size,
yeah.
no, meaning it's the
Yes,
linear
so,
dimension. It's the area of the cluster. This is 2D, right?
Yes.
So this is the
yes.
area of the cluster,
no,
or the number of radius of the cluster?
Radius of the cluster.
It's the radius. Growing linearly. I mean, first of all, you sort of drawn a linear fit through it, but oh God, excuse me. No, it is on non-silent. You've drawn a straight line, but actually there's a fair amount of curvature. And wouldn't you expect the domain growth law normally to be something more like t to the 1/3 or something?
Maybe the best way to look into it, to look into the autocorrelation of this cluster size. Then only
Right.
I can look into how much more, because this is still the work ongoing. So we are now trying to look into the autocorrelation. Then the domain of one type of dependency, we get better insight into that.
Okay, let us thank the speaker.